All right, last part of this lecture. So we've looked at the difficulties with geospatial data, how they're a little bit weird. They don't look like regular data. They don't look like regular files. We've looked at a couple of places to get data, and now I want to talk a little bit about how do I know if that data is any good. So you may have heard this phrase or seen this acronym before, GIGO, which stands for garbage in, garbage out. If you get crappy data, you're going to get crappy map products. So how do you know if your data is crappy? Some of that has to do with a visual inspection. One of the key things that we're looking for is accuracy. And accuracy has to do with how well the data or the map match up with true or accepted values. This is a pair of maps here from Google. In many places in the world, Google doesn't have access to the most up-to-date information, and so they use highly generalized data from older maps or information collected from a variety of sources. And so on the left-hand side, you can see that the border here between Nicaragua and Costa Rica is just kind of blobby and scribbled in there a little bit. And this unfortunately came to light when the government of Nicaragua decided that this meant that this portion of this forest was their territory, and so they showed up with the military. Fortunately, a conflict was avoided, but you'll notice that Google now has, not only have they corrected the boundary, but they now have this disclaimer that shows up in the corner of their maps that has terms of use, which basically says you can't use this for a military occupation. So Google Maps, we find them to be really helpful. We use them all the time, but they're not always completely accurate in all locations. And it's important to understand any other data that we collect or download from some resource, what level of accuracy we should expect from that data source. The other side of this relationship is precision. And precision is the level of exactness. So you could have something that's fairly accurate but not very exact. One way to maybe think about it is in the number of decimal points. Or if we go back to the Minecraft data earlier, the Minecraft blocks are 1 meter blocks. So 1 meter by 1 meter for each block in this data, which means that I might get a very accurate representation of this landform, but it's not going to be super precise. Skyrim, on the other hand, has much higher resolution and much higher precision, and so this tree looks incredibly realistic because it's very, very precise. Can you have accuracy without precision? Yes. The example on the left, Minecraft, accurate but not very precise. Can you have precision without accuracy? Absolutely. You could have a tree that looks absolutely marvelous, like this one in Skyrim, and it could be in the wrong place, or it could be the wrong species. So the two are not mutually exclusive, but nor are they mutually supportive. So what you want to try to do is get the best of both worlds, right? We want to be as precise as possible. We want to be as accurate as possible. Sometimes that's not, that's a limitation of cost. Sometimes it's a limitation of our ability to collect the data. There are lots of things that impact our ability to have perfectly accurate, perfectly precise data. Which is, it's an unattainable goal. It's a goal you should have, but it's basically unattainable. So you should always try to get data as precise and as accurate as you can manage, and try to get up toward this corner of the graph. We can't get perfect data. It's not going to happen. There's always going to be some level of error. So we have to acknowledge that and do what we can to minimize it, right? So there are three basic sources of error that we have to think about when we're collecting data and even when we're analyzing and processing data. The first one is positional, right? This is geographic data. If it's in the wrong spot, it's a positional error. So that could be either an accuracy problem, it could be in the wrong spot, or it could simply be imprecisely measured, right? That border of Nicaragua and Costa Rica was sort of in the right area. If you zoom way out to, like the globe level, it's going to be close enough for that purpose. But zoomed in, it's not precise enough. Attribute data, right? We mentioned that you can have spatial data that has attributes attached. So this could be inaccuracy or imprecision in collecting the non-spatial elements of your data. Let's say that you're doing an observation of wildlife and you're doing counts and you can't quite see, there's maybe one animal behind another one and you can't tell, and so it looks like there's two, so you count it as two and it turns out there were actually three. Right, that's going to be an inaccuracy or an imprecision in the non-spatial data. Or maybe the bird that's behind the bird that you're counting is not the same species, and you didn't realize that and you counted it that way. And then last but not least is conceptual error, which is essentially flawed logic. So this is, regardless of whatever condition your data is in as far as accuracy and precision, conceptual conceptual errors mean that you have made an error in making a decision about something. So as an example, the planet is warming up and therefore the glaciers are melting and therefore river flow decreases. That doesn't make any sense, right? The glaciers are melting, there is more water available, the river flow should be increasing in areas fed by glaciers. So you want to be careful of these kinds of things. They can be harder to spot, but we see them all the time. All right, here's an example of a graph that was on the internet not long ago. What do you spot that's incorrect in this graph? There are lots of things to choose from, so you may spot something different than someone else spots, but a couple of different things that I'll just call out here, and this is by no means an exhaustive list, right? Between 1947 and 1979, so that's 32 years, and then we go 1979 to 2009, so that's 30 years. So we're not comparing the same size interval. Then we're talking about the bottom fifth of the population, and then the top 1%. There's nothing here that shows the bottom fifth of the population. So this number and this statistic, bottom fifth of the population rose by 122%, aren't here anywhere, right? What it's trying to do, though, is make things look super scary. And they do, right? This looks alarming, right? The 1% is just taking off with all of this money sitting on piles of gold, counting it in their living rooms, whatever it is that they're doing, right? And the 99% things are just getting a little crappier all the time. So basically this first line is a red herring because this isn't relevant to this graph at all. And then there's also this weirdness here where we're talking about these two dates and then we're talking about two different intervals happening, right? So it's meant to alarm you, it's meant to scare you, but don't stop there. Keep digging and find out what's actually true. This is another one. This is a fantastic website. I love this Spurious Correlations website. This guy has all kinds of fun examples of this. And basically what you do is you take two data sets and you stretch the axes until they look roughly the same, right? So here we can see clearly that if you eat a lot of cheese, you run a high risk of dying by being tangled in your bed sheets, right? The conclusions are obvious. They're obviously connected. Of course, that's completely ridiculous. What's happened here is that cheese has this curve, and people dying tangled in bed sheets have this curve, and they've simply lined up the axes so that they match. And you'll see a lot of graphs like this. And we're in an election year, and so it's only going to get worse, right? So lots and lots of correlations are drawn from things. Oftentimes you'll see things, oh, this happened, therefore this happened. For example, the recent post office situation where equipment's being dismantled, and a lot of people have been claiming, oh, they're targeting democratic cities. And it's like, well, they're targeting the largest cities. For whatever reasons you want to go into, the effect on the mail is more dramatic when you target large cities. It really doesn't matter whether it's a Democratic city or a Republican city. The fact is it's a large city, therefore the mail is going to be greatly impacted by that slowdown. So lots and lots of things, like I said, particularly as we near the elections, you're going to see lots of people flinging blame in lots of directions, and sometimes it's warranted. But you always want to ask that question, is correlation causation in this case? Okay, so that's part of telling how good your data is, right? Is it accurate? Is it precise? And does it make sense? All right. A couple more things for you to do this week. Reading the chapter, you've got a discussion post and a syllabus quiz to come up. And in the bottom of this discussion where all these lectures are, there's a space down there you can ask questions, and I'll come back and respond to those throughout the week. Thanks for listening.